card. Shared screen. That's you guys. Why? Oh, Zoom. I hate you sometimes. Okay. 4.5 rational functions. So 4.1 through 4.4, we've exhausted everything we could at this point with polynomial functions. And now in 4.5 and 4.6, we learn about rational functions. A rational function is when you have a function of the format p of x over q of x where p and q are both polynomial functions. And my dog is going to town on a toy, so I apologize if you hear strange noises. Who's good? Who's a good boy? Yes, you are. So when you have a polynomial over a polynomial, you've created a rational function. The comment is, and we didn't have a question like this on the test because it wasn't necessary, because it was going to come up here anyways. The comment is that, notice, we have a fraction, and so tell me about the domain. What can't happen in that denominator? The domain is all values of x except where q of x equals, oh, that's a g, q of x equals 0. So same stuff that we did day 1. We just now know the formal name is called a rational function when you have a polynomial over a polynomial. Now, as an example, let's consider the rational function 3x plus 7 over x plus 2. This next part that we're going to do, that I'm going to show you, is literally demonstrative purposes. This fraction is the same thing as 1 over x plus 2 plus 3. And the way you know that is because if we were to make a common denominator here and make it one fraction, you would get back this guy over here, 3x plus 7 over x plus 2. Is that Mom? Hi, Mom. Anyways. You've been embarrassed! Anyways, notice by writing it as 1 over x plus 2 plus 3, this is now a transformation of 1 over x. It's actually very similar to your test. Your test had minus 2, I think it was. This one has plus 3. So if we were to graph this as a transformation, the x plus 2 would say move left 2. And the plus 3 would say move up 3. So our new vertical asymptote would be at x equals negative 2. And the new horizontal asymptote would be at y equals 3. And the graph looks something like this. Oh, squishy graph. That's okay. So the reason it's broken up that way is just to see it as a transformation. We don't know yet how to look at this thing and know exactly where the asymptotes are. And as a comment, in section 9.8, we will learn how to break up a fraction. So that's what's coming up. So now let's talk about where asymptotes are coming from. Don't look at that. because that's not at all what we need. This is demonstrative purposes. You don't have to follow along. Just I'll tell you what the part's the important part. So all I'm doing is put the function in the calculator. Let's first start with the vertical asymptote, which is at x equals -2, and we know that by transformations. But now we're going to talk about it. What does that mean numerically? What's going on? So I'm purposely putting in numbers in for x, and I want you to see what happens to the corresponding y. So I'm going to put numbers that get closer and closer to -2. I'm going to start to the left of -2, meaning I'll start with -3 and -2.5 and -2.1. And as I'm doing this, I want you to look at what the y values are doing. Notice the calculator runs out of space here, so it didn't put the extra 0 there. But look at these y values, 2, 1, -7, -97, blah, 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 blah. As x gets closer and closer to -2 on the left, what happens to the y values? Are they going somewhere?
It's like they're multiplied by they're multiplied by 10.
Yeah, it looks like they're increasing by a factor of 10, sure. And then will that change? Will that ever stop? Will it stop at a number, or will it just keep going forever?
I think it'll keep going forever.
Yeah, and notice it's getting more and more and more and more negative. In other words, it's going towards negative infinity. And likewise, if I approach -2 from the right-hand side, so -1, -1.5, -1.9, -1.99, what's happening to these y values here? Are
It's
they
going
stopping
up.
somewhere? Are they go on for it? Charmaine?
No, I was about to say it's going towards positive, where it's positive infinity.
Perfect. So, and we can see that graphically now. Notice as we approached -2 from the left, the corresponding y values just decrease forever and ever. As we approach -2 from the right, the corresponding y values increase forever and ever. So when this phenomenon occurs, this is where a vertical asymptote comes from. And let's write that down. As x approaches a number a, oh, you know what? I'm so sorry. There's a stupid word I need to start with. If as x approaches a number a, sorry about that, y approaches infinity or y approaches negative infinity, x equals a is a vertical asymptote. So as x gets closer to a number in either direction, doesn't matter, and at the same time y's are shooting off towards infinity or negative infinity, that's where a vertical asymptote comes from. Okay. Let's talk about a horizontal asymptote. So I'm going to put in numbers in for x. The numbers I put in for x are going to get bigger and bigger. So now x is technically shooting off towards infinity. What's happening to these y values? Is it approaching a number or is it shooting off towards infinity?
It's approaching a number.
Which number?
3.
Yeah. And then if we went in the other direction, -1, -10, -100. For this one, notice it happens to be approaching the same number. It happens to be approaching 3 as well. So notice it's the flip. And what I mean by that is here for the horizontal, as x gets really, really big, the y's get closer and closer to 3. As x gets really, really small, the y's get closer and closer to 3. And that flip is now y is approaching a number as x approaches infinity. So exact opposite of what we already wrote. So if as x approaches infinity or x approaches negative infinity, y approaches a number, we usually use the letter b associated with y. Y equals b is a horizontal asymptote. So this is where asymptotes come from. One variable, I apologize. This is where horizontal and vertical asymptotes come from because there's other types. One variable approaches the number and the other variable approaches infinity or negative infinity. However, that doesn't really help us find them, which is the rest of the section. So let's talk about finding vertical asymptotes, and they are paired up with holes. Oh my gosh. Oh no. I should have been a doctor. Handwriting's wonderful. That does say finding vertical asymptotes and holes. There are 3 steps. Step 1. Find the values of x that make the denominator 0. Step 2, plug these values into the numerator one at a time. And there's 2 possible outcomes. The first one, if you do not get 0, that value leads to a vertical asymptote. Oh no. If you do not get 0, that value leads to a vertical asymptote. If you do get 0, that value leads to a hole. A vertical asymptote is a line, so when you are answering vertical asymptotes, make sure it's of the format x equals a number. Don't just say 5 is a vertical asymptote. That's not true. 5 is a number. X equals 5 is a line. That's good. A hole is a missing point. Because it's a point, it has the format x comma y. So when you are asked to give an expression for a hole, make sure you write it as an ordered pair. Let's do an example that has both a vertical asymptote and a hole. Side note, a graph can have multiple vertical asymptotes, multiple holes, a mixture of the two, or it could have neither. Any of that's kosher. Oh no, and now oh no. Oh, I have to do this in my head? What's the point? Don't write it down yet. I'll tell you when it's safe. All right, safe. I don't like it, but it's fine. Okay. So step 1, we will determine the values that make the denominator 0. In other words, we're finding the numbers that aren't in the domain. So we're going to put x squared plus 7x plus 6 equal to 0. How doth that factor?
Could that be x plus 1 and x plus 6?
It can. So the numbers that make the denominator 0 would be -1 and -6. So that's step 1. Questions on step 1? Okay. Step 2, one at a time, we're going to put in these numbers. So I'm going to put in -1 in for all of the x's in the numerator. So we'll have -1 quantity squared plus 2 times -1 plus 1. And what does that give us? How many pineapples am I holding up?
0.
There you go. Very good. So we stuck in -1 into the numerator and we got 0. If you get 0, that value leads to a whole. So we know that the y-coordinate of the whole is -1. We just don't know what the x-coordinate is. Well, here's the deal. Typically, to find a y-coordinate, if you know the x-coordinate, you plug -1 back into the function. We can't do that here because we have just demonstrated that -1 makes the numerator 0 and the denominator 0. So technically, -1 makes the function 0 over 0. 0 over 0 is what's called indeterminate form. You don't have to worry about that for now. That's a calc thing. They'll use that terminology and explain it then. But the whole idea is we don't know what that is. There's a way to figure out which specific thing it is. And what you do is a little bit of side work. I'm going to do it in a different color here. You take the original function and you factor the numerator and denominator. The numerator factors as x plus 1 quantity squared. The denominator we factored as x plus 1, x plus 6. Once it's factored, you reduce the function. So notice we have 2 x plus 1s upstairs, and we have 1 x plus 1 downstairs. So notice we can cancel one of each. So this function reduces down to x plus 1 over x plus 6. The thing is what we have in black there is the original function with a hole. What we have in green is the original function with that hole filled in. So that point that wasn't there is now there. These are not the same thing because one has a hole, one doesn't. But if you were to graph them in the calculator, they would look exactly the same because the calculator does not say, hey, there's a hole here. With that hole filled in, then what you do is you reevaluate it now, in this case at x equals -1. So I'm going to put -1 into the numerator and -1 into the denominator. Upstairs, -1 plus 1 is 0. Downstairs, -1 plus 6 is 5. 0 over 5 is 0. Which means our whole is at -1 comma 0.
That's it. I mean, I keep talking while I get the shot.
Jamel, if you can mute, please. Jamel, are you there? Jamel, are you there? Jamel, are you there? Jamel. Jamel, I think I can mute him. Mute. I did it. Don't tell him. Okay. So again, if you have a whole, reduce your fraction, and then reevaluate your fraction at the x-coordinate of the whole. Now we got to do the same thing for x equals -6. We put in -6 in for all of the x's in the numerator, and we ask ourselves if this equals 0 or not. -6 squared is 36, minus 12 plus 1, that doesn't equal 0. So we did not get 0 at -6. So what is x equals -6? If you do not get 0, that value leads to a
Vertical asymptote.
vertical asymptote. So again, don't just say -6. Please say x equals -6. Muy bien. All right, that's vertical asymptotes and wholes. They are accompanied by horizontal asymptotes, and their counterpart is oblique asymptotes. So let's talk about horizontal and oblique asymptotes. Oblique asymptotes are the ones you have to do like the side crunches for that nobody likes to do. There are 4 cases here, and we're actually going to do it all by example. So I'm just going to write a bunch of stuff down. Ugh. Ugh. If you could write that down while I pretend to play the recorder. So horizontal and oblique asymptotes, even though there's 4 cases and it appears like it's going to be a lot of work, it really, 3 of these 4 cases, you can just look at it and know what the answer is. Only one of them you actually have to do any work. The first case is our f of x here. In f of x, notice the degree of the numerator is smaller than the degree of the denominator. If the degree of the numerator is smaller than the degree of the denominator, then y equals 0 is the horizontal asymptote. We'll go through all 4 cases and then I'll talk about why things are the way they are. In g of x, tell me about the degrees of the numerator and denominator.
The degrees are the same.
Excellent. If the degree of the numerator equals the degree of the denominator, then y equals, I have to write it like this, the ratio of leading coefficients is the horizontal asymptote. The ratio of leading coefficients. Ratio is just fancy talk for fraction. What's the leading coefficient in the numerator?
Two.
Good. And the denominator?
-7.
Good. So the ratio of leading coefficients would be -2/7. That would be your horizontal asymptote. H of x is actually the one that requires work. If the degree of the numerator is 1 more than the degree of the denominator, you have an oblique asymptote. So horizontal asymptotes go left and right, vertical go up and down, oblique are your slanted. As far as finding an oblique asymptote, you have to use division. Now, since for this one specifically, we are, I'm so sorry, I should have had this prepared, but I saw something shiny. Nope. Oh well. As far as this one is concerned, since we're dividing by a linear, we can use synthetic division. If we were dividing by a quadratic or higher, you'd have to use long division. So for this one, we can sneak this in. So we're dividing by x plus 6, which has a 0 of -6. So -6 would go in the little box there. And then our quotient would be 3, -5, 1. I'm sorry, I said quotient. I meant dividend. You would drop the first number, multiply by what's in the box, add, and if all you're finding is the oblique asymptote, stop. You don't need to go as far as the remainder, because the oblique asymptote is brought to you by the quotient. So in this case, it's y equals 3x minus 23 would be the oblique asymptote. So again, if the degree of the numerator is exactly 1 more than the denominator, oblique, and then use division to find it. So if you remember on your midterm, number 14, you had to do long division because it was a cubic divided by a quadratic. And then, if I remember correctly, the quotient was x plus 5. So then the oblique asymptote would have been y equals x plus 5. So the oblique is the only one you have to do work on. For j of x, notice that we're in the we're in a case that's not like the other three. We're not less than, we're not equal to, we're not exactly one more, we're more than one more. So if this is the case, otherwise, you have no horizontal or oblique asymptote. Key thing to understand though is you can have a you can have a vertical asymptote and a hole in the same function, but you cannot have a horizontal and an oblique asymptote at the same time. You either have one or the other for this category. Okay. So real quick, going back to this one here. What type of, do we have a horizontal? Do we have an oblique? If so, where is it at?
Wouldn't that be horizontal because of the degrees? So
Yep.
the x squared at the numerator and x squared at the denominator.
Perfect. Yep. So because the degrees are the same, it's the ratio of leading coefficients. So 1 over 1 is 1. So y equals 1 is your horizontal asymptote. Very good. So then there are 2 videos for the last part of this section, and that is basically putting everything together. Finding intercepts, finding vertical asymptotes and holes, oblique asymptotes, and depending on the problem, also sketching a graph. Let's do a quick one. Oh no. Oh. No. That's fine. So suppose we have this function f of x equals 2x plus 3 over x squared plus 5x plus 6. We're going to find the domain. We're going to find x-intercepts. We're going to find y-intercept. We're going to find vertical asymptotes, holes. We're going to find horizontal oblique asymptotes. And we won't find a graph because this one's ugly to graph, but we'll talk about the graph just in case it's in your homework. So domain, to find the domain of a rational function, remember, set the denominator equal to 0. How does this factor?
That'd be x. Oh, wait, never mind.
Nope. Did you say it? 2 and 3? Yeah, you got it. So x cannot equal -2. X cannot equal -3. Awesome. When you are moving forward, especially for parts 2 and 3 here, you have to keep the domain in mind, and we'll talk about y in a second. X, so this is a sticking point. X-intercepts occur when the function equals 0. A fraction equals 0 when the numerator is 0. So we only have to put the numerator equal to 0. So one more time, you only consider the numerator if you're talking about x-intercepts. Do not carry that over to any other part. Well, here, if we solve for x, we get negative 3 halves. Our x-intercept is negative 3 halves, comma 0. But as a comment, one thing we would have to check, which we're okay here, is negative 3 halves is in the domain. So, for instance, if in step 2 here, we found x to be negative 2, we cannot say that negative 2 comma 0 is an x-intercept because negative 2 is not in the domain. Things have to be in the domain in order to be x-intercepts. A y-intercept occurs when x equals 0. So again, x-intercepts only, for this work, only refer to the numerator. Y-intercept, you go back to the entire function. Students tend to only put it into the numerator. You need to put 0, fixed it. You need to put 0 in for all of the x's, upstairs and downstairs. Upstairs you get 3, downstairs you get 6, reduces down to 1/2. So 0, 1/2 is your y-intercept. Now as a comment, in order for a y-intercept to occur, the number 0 has to be in the domain because that's the x value. If 0 is not in the domain, you can't have a y-intercept. And the work would fall out anyways because you would get like something like 7 divided by 0, which you would say does not exist. So even though number 1, we don't see it, it does affect everything else. Questions so far? Okay. Vertical asymptotes and wholes. Remember that the first step of a vertical asymptote and whole is to find the numbers that make the denominator 0. Well, we already did that in step 1. Those numbers are negative 2 and negative 3. So don't redo the work. It's already done. So one at a time, we'll put in negative 2 into the numerator. And we're going to ask ourselves, does this equal 0? Nope. So that means x equals negative 2 is a vertical asymptote. Oh, that was weird. I don't know why I did that. I can make a v. Nailed it. So x equals negative 2, vertical asymptote. Do the same thing for negative 3. 2 times negative 3 plus 3. Does that equal 0? Nope. Very good. So this is also a vertical asymptote. So this graph has 2 vertical asymptotes and no wholes. Just how I like my donuts. Horizontal or oblique asymptotes. Remember, those are mutually exclusive. You have one or the other, but not both. The degree of the numerator is 1. Denominator is 2. So the numerator's degree is less than the denominator's degree. So there's no work. Y equals 0 is your horizontal asymptote. Now, we're not going to, for this one, we're not going to do a proper graph. One of the videos, we are able to do a graph because it's a transformation of 1 over x, so definitely watch that. But as far as all we know we have an x-intercept at negative 3 halves, comma 0, so right there. We have a y-intercept at 0, 1/2, so about right there. We have a vertical asymptote at negative 2. And at negative 3. Ugh, that's awful. These are really close to one another. And we have a horizontal asymptote, which happens to be along the x-axis because it's at y equals 0. This is not enough information to sketch a graph at all. So we would have to plot more points at this level. In calc, you learn how to do a full rational function graph and every other type of function using calculus. But this thing probably does something crazy. I have no idea, to be very honest. If I were to guess, it probably does something like this. It's like there's like a little U shape there, guy. And then this is pretty interesting here because I think what it does is it crosses the horizontal asymptote, goes through that point, and then gets close to the axis. Something insane. But that's just based on guessing. We'd have to look at a calculator to do it. I don't think there's any ugly ones like this where you'd have to graph them on your homework. But if there are, you'd have to rely on the calculator and or make a table and plot more points, which is beyond what I would want. Yep. There's the graph. So the reason it's interesting is sometimes students come in with the idea that you can never cross an asymptote. You can cross a horizontal, you can cross an oblique, you can never cross a vertical. So we did happen to cross a horizontal here. And the only other thing I'm going to say is the idea of why horizontal and obliques are the way they are. And it goes back to the idea of division and that these guys are polynomials. So if you remember, we had this thing called the leading term test, which said only the leading term mattered. Nothing else mattered as far as what dictates the arrowheads. So for this one here, for example, as x got really, really big, the numerator is just like the leading term. The plus 1 just falls off. And the denominator is like its leading term, x cubed. X squared over x cubed is the same thing. It reduces down to 1 over x. So as x gets really, really big, what happens to this fraction as a whole? So like if you had 1/2, 1/3, 1/10, 1/1000th, 1/1,000,000th, the fraction as a whole, what happens to it?
Wouldn't it get smaller?
Yeah.
I mean, smaller.
Yeah, and it gets smaller, but it doesn't get smaller forever. It doesn't approach negative infinity. It actually approaches 0. So this is where the horizontal asymptotes come from, is that it's the whole idea of things are just approaching their leading terms, and sometimes the leading terms reduce, and then it goes to 0, or here you'd have you'd have 2x squared over negative 7x squared, so these just cancel, so it goes to 2 over negative 7. Here you differ by 1, so it's approaching a linear function. And here it's not approaching a line anymore. This guy does have an asymptote, but it's a cubic function because 4 over 1. 4 minus 1 is 3. We don't get into it. Calc doesn't even get into it because it's not that important. All right. That is 4.5. All right, 4.6, hopefully we'll go quick because it's already 7 o'clock. Oh no, I didn't take my pizza dough out. Oh no, the humanity. 4.6 is polynomial and rational inequalities. We'll do one example of each, and we'll learn how to do it per example. Let's start off with a polynomial inequality. Suppose we had x squared minus 7x minus, hold on, wait for it, minus 60? No, that's too much. I don't like that. Let's say minus 3x minus 40 is greater than or equal to 0. Okay. There are several steps here. The first step is to solve the related equation. Meaning that instead of the inequality, we're just going to put an equal sign. If I give you 1, it's going to factor. Also, it's going to be in standard form, meaning everything on the left, 0 on the right. There's no sense on the test to make you make common denominators and all that junk. So you don't have to worry about that. I can't guarantee that for the homework, though. So notice this factors as x plus 5, x minus 8, which gives you the values negative 5 and positive 8. Step 2, we're going to draw a number line. And divide it into sections. Using the values, from step 1. In fact, the remaining steps all deal with this number line. So there's negative 5, there's positive 8. Now, if you have colored pencils, this is the perfect time to use them. If you don't, that's fine. But please note what we're about to do, you don't want to be confused with your work. Notice here I'm using little tick lines. And what I'm about to do is use dots. You want to make some form of distinction because the thing with the dots, once you get what you need to get, you don't use them anymore. So step 3 is pick a test number from each section and determine its sign. So this section here are all numbers to the left of negative 5. I can choose a number in there. I can choose negative 6. This section here are all numbers between negative 5 and 8. I can choose 0. And this is all numbers bigger than 8. I can choose 9. These 3 numbers are one-off. Once we use them, we don't consider them anymore. We only need to focus on the negative 5 and 8 after this step. So there's our test numbers. We did this portion. Now as far as determine its sign, what that means is because it's already in standard form, we're going to replace all the x's in this expression with those numbers one at a time. Meaning if I do negative 6 quantity squared, minus 3 times negative 6, minus 40. All that matters is this a positive number or a negative number? 36 plus 18 minus 40 is still positive. And you do the same thing for 0 and 9. I will tell you 0 gives you negative, 9 gives you positive. And Red Bull does not give you wings. Do not assume that the signs will alternate. In fact, one of the video examples has a sign that does not alternate. And there's a reason for it, and it goes back to multiplicity, the whole touch cross thing that we talked about earlier. So you need to check every test number. Now that we have these signs, the negative 6, 0, 9 are not important. So please ignore them. So step 4 says the solution includes all values whose sign agrees with the inequality. Inequality. And there's a little caveat. If there's an equal sign, you want to include the values from step 1. Meaning if it's not strict. Well, our inequality is greater than or equal to 0. Greater than or equal to 0 says we want the positives. So that's this section here and this section here. The first section goes all the way left to negative infinity and goes up to negative 5. But because our inequality has an equal sign, we want to include the negative 5, so we say bracket, union. The next section starts at 8. Same deal, our inequality has an equal sign, so we start with a bracket. And it goes all the way to the right, so infinity. So these are the values of x that make x squared minus 3x minus 40 greater than or equal to 0. Please note, it's not that the x's are greater than or equal to 0. It's that when we plug it into the expression x squared minus 3x minus 40, that number is greater than or equal to 0. Questions? Okay, so that's a polynomial. We did a quadratic here. There's a quadratic and a cubic in the videos. So watch that. Oh, I don't know what that was supposed to do. Copy. So let's talk about a rational one. We actually modify our notes a little bit. And we'll do a very basic one here. There's 2 videos for you to watch. Suppose we had, I don't know, x minus 4 over x plus 3 greater than or equal to 0. The numbering is going to change here. Step 1 is to write in standard form. To be honest, that should also have been step 1 in the previous one, but I'm just telling you I'm going to always have it in standard form. In your homework, though, I think there's one that's not in standard form for rational, so just FYI. Step 2 is to determine where the numerator is 0. So notice our step 1's already done. Everything is on one side, 0's on the other. Step 2, we're going to set the numerator equal to 0. And notice we get 4. Step 3 is determine where the denominator equals 0. So the denominator, set x plus 3 equals 0. And we get x to be negative 3. Step 4, draw a number line and divide it into sections using the values from steps 2 and 3. Notice again we have 3 sections. The problem is don't always assume that we'll always have 3 sections. You can have as many sections as you need to. The next step is the same. Pick a test number from each section and determine its sign. So a number to the left of negative 3 could be negative 4. A number between negative 3 and 4 could be 0. And to the right of 4 could be 5. You put in these 3 numbers into the entire fraction as long as it's in standard form. Again, you have to do every single one because there could be signs that don't alternate. This one happens to also be plus minus plus, but that is 1,000,000% coincidence. You need to test every single one. So that was step 5. Step 6 is the solution. We have a modification. The solution includes this should really say sections, so I apologize. That's fine. All sections whose sign agrees with an inequality. If it's non-strict, include only the values from step 2. Never include the values from step 3. Because if you did, you'd cause division by 0, which is not good. So we have greater than or equal to 0. You know what? I'm going to change this. It's not going to affect any of our work. Let's make that less than or equal to 0. So we have less than or equal to 0. Less than or equal to 0 means we want the negative section. We have a negative section here. That goes from negative 3 to 4. So we want those numbers, the numbers in between them. But notice negative 3 came from the denominator, so no matter what the inequality says, it has to get a parenthesis. 4 came from the numerator, and because the inequality is not strict, we throw a bracket on it. All right. All right. Very good. Okay, that's chapter 4. How much time do we have? 6 minutes? Do we go to 7:25 or do we go to 7:20? I can never remember. 7:25? Yep. Okay, so 11 minutes. Here we go. 5.1, inverse functions. The whole point of an inverse function is to undo another function. So for instance, if we had the function x plus 3, what this function is saying to do is whatever you give it, it's going to add 3. So if you give it 7, it gives you 10. Give you 12, gives you 15. What would undo adding 3?
You would subtract 3.
Yeah. So if I called another function g of x and defined it as x minus 3, now what happens is these two functions undo each other. We'll see what that undo means later on. But that's the whole idea of a function. Two functions are inverses. This is layman's term. Two functions are inverses if they undo each other. Formally, instead of writing a g of x here, we have notation for the inverse. The inverse of f is denoted by the function, whatever the function name is, so in this case f, and what looks to be raised to the negative 1 of x. So that's pronounced the inverse of f, or f inverse. This is not the reciprocal. So when you see a negative 1 exponent on a function, that says the inverse. However, not all functions have inverses. For instance, if I had f of x equaling the square root of x, you might think that g of x is x squared. So for instance, if I found g of negative 5, that would be negative 5 quantity squared, which would be 25. So that means under the function g, the number negative 5 went to the number 25. So if I find f of 25, that would be the square root of 25, which is 5. So did the function f take 25 back to negative 5? No. So these two functions undid each other, but these two did not. And the reason the purple ones did not work is because they do not have a special property of functions, and that is what's called a one-to-one function. In a one-to-one function, this is layman's terms, every x goes to 1y, and every y comes from 1x. And the reason that was a problem for the stuff in purple there is because notice the number 5 and negative 5 when squared turns into 25. So two different x values gave you the same y value, and that violates this. So x squared is a function, but it's not a one-to-one function. Mathematically, the way we define a one-to-one function is if for all a and b in the domain where a does not equal b, f of a does not equal f of b. It's very notational. We'll walk ourselves through it. If for all a and b in the domain where a does not equal b, f of a does not equal f of b. So what this says is different x values give you different y values. And that was the problem up here. Here we have different x values, 5 and negative 5, but we ended up with the same y value. So, In order to have an inverse, the function must be 1 to 1. How do you know if a function's 1 to 1? Well, the stuff in black here is a proof of it, which we don't really get into. We tend to look at the visual stuff of it, the visual end of it, and the way you can do that is what's called the horizontal line test. So we know that the vertical line test finds functions. The horizontal line test finds 1 to 1 functions. The horizontal line test works pretty much like the vertical line test. The whole idea is if you can draw a horizontal line that hits the graph more than once, then that's bad. So if you can draw a horizontal line that hits the graph more than once, it's not a 1 to 1 function. So our very first graph is x squared. Just to put some numbers in, 5 and negative 5 both give you 25 for y. So that visually is showing you that it's not a 1 to 1 function. The second graph is x cubed. Notice no matter what horizontal line I draw, I'm only hitting the graph once, which makes it a 1 to 1 function. But don't assume that just because it's cubic, it's automatically 1 to 1. This guy is f of x equals x cubed minus 9x, for example. And I can draw the horizontal line right here along the x-axis. And notice I hit it 3 times. So this is not 1 to 1. So, as far as finding inverses, we're going to have a couple of types. For instance, I can give you a set of ordered pairs. So if I had 3, 2, 6, 1, 0, 5. So this was our function f. When it's just a bunch of ordered pairs, the inverse is very nice to find. And by the way, if you have to leave at 25 after, that's fine. I'll just post the video. I'm just going to keep talking so it's a complete set. But if I'm just talking to myself, that's fine too. Anyways, the original function f is taking 3 to the number 2. So the inverse is going to undo that. So that means it's going to have the point 2, 3. The original function f takes 6 to 1, so the inverse would undo that by taking 1 back to 6. And lastly, if f takes 0 to 5, the inverse takes 5 to 0. So let's look at these two functions here. Let's look at the domain of f. Remember, domain is the x values. What's the domain of the original function f?
Three, 6, and 0.
3, 6, 0. Good. And what's the range of the function f? Range is the y values.
The 2, 1, and 5.
2, 1, 5. Good. Excellent. And now let's look at the function inverse. Notice the domain of f inverse is 2, 1, 5, and that happened to be the range of the original function. Likewise, the range of the function inverse, 3, 6, 0, happened to be the domain of the original function. And that will always be true. If the function is 1 to 1, the domain of the first of the original function is the range of the inverse, and vice versa. So the domain of f is equal to the range of f inverse. And the range of f is equal to the domain of f inverse. Okay. I'll try to wrap up in 10 minutes. I apologize. Questions so far, first off. Okay. So then, as far as finding inverses, we looked at ordered pairs. That can continue into a graph. For instance, let's suppose we had let's make that the point -2, 0. And we'll make this the point -1, 1. And we'll make this the point 3, 2. And we'll just connect it with with line segments. I cannot believe how well that worked out. So -2, 0, -1, 1, 3, 2. And I'm just going to call that f. We're going to graph the inverse. This is just like the previous example where all you do is permute the coordinates. So if the original function takes -2 to 0, the inverse takes 0 to -2. If the original function takes -1 to 1, the inverse takes 1 to -1. And lastly, if the original function takes 3 to 2, the inverse takes 2 to 3. And then we'll connect these with line segments like we did for f. And this is the graph of f inverse. Several things to note. Number one, you should note that the graph of the function and its inverse are reflected over the line y equals x. Always, always, always. So now if you go back and think about the graph of x cubed and the cube root of x, that's why they look alike. One's just reflected over the line y equals x, because those are inverse functions. That's comment one. Comment two, even in graphical form, the statement about the domain and range has to hold up. So notice the blue graph from left to right goes from -2 to +3, and from top to bottom goes from 0 to 2. Looking at the purple graph, from left to right goes from 0 to 2, so that's the domain of the inverse, and the range from top to bottom goes from -2 to 3. So when you're graphing your inverses, they need to follow that. Okay, a couple more comments, and then I'll, because we're over time, I'll just ask you to watch the videos. However, there's 3 examples for this next part, and that next part is finding the inverse algebraically. So keep this in mind while you're watching those videos. There are 4 steps. The first step is to replace f of x with y. The next step is to interchange x and y, meaning every x becomes a y, every y becomes an x. 3 is solve for y. And 4 is replace y with the symbol f inverse of x. Steps 1, 2, and 4 are purely cosmetic. Step 3 is where the fun's at. We can actually do an extremely quick example. Let's actually start with the very first one. And again, there's 3 more for this. So the first thing we talked about was x plus 3. So step 1, instead of f of x, we put y. Step 2, y becomes an x becomes a y. Step 3, we would solve for y by subtracting 3. And step 4, instead of y, we write f inverse. And that's what we talked about anyways, that if the original function adds 3, the inverse has to subtract 3. The last part is the real definition of an inverse. F and f inverse are inverses. I know this is weird. Why are we calling it f inverse if it's not an inverse? It's like naming your child doctor and they turn out to be a lawyer. How disappointing for your family. But these 2 functions are inverses if the following are true. F composed with f inverse of x gives you x. And f inverse of x, f inverse of f of x gives you back x. This is the very streamlined definition because we're short on time. In other words, this says that if you put one function inside of the other and simplify, you have to get x. And that has to go in both directions. If you don't get x, then they're not inverses of one another. But in your homework, please be careful. If it says show that in mathematics means it's already true, demonstrate it for yourself. So you should be getting x as your final result here. The other comment is you have to worry about domain. You have to worry about the domain of the inverse function. That's just for by the way, so I said that I said it. It's not too important for what we're doing. It's more important for trigonometry. All right, that's enough torture. Next, I'll email you on Sunday. Hi, Marsh. Do you want to go outside? Yes, you do. I'll email you guys on Sunday to see if I got jury duty. And then we'll go from there. If you have any questions, you know what to ask. All right. Have a great evening. Thanks for sticking around.